All right, hey everybody, Mr. Fortin here. I got to film a correction video now for you guys. Now, in the lesson video, when I was doing the classroom exercises, I did number 10 here, which is, are all isosceles right triangles similar to one another? And I really kind of struggled in that problem. If you kind of saw that one, I struggled and I was like, how do you figure this out? How would you know this? And I had to break it down and I settled on an answer. And I filmed that video yesterday, and then I got to thinking today. I graded a few exit tickets, looked at them back, and then I was driving to daycare, right? Driving to pick up my daughter at daycare, and it hit me. I did it incorrectly. I got that one wrong because it turns out that all isosceles right triangles are similar to one another. Yes, they are similar to one another. They are, okay? And we want to check it out here. I'm drawing these three triangles right here, and they sure as hell look similar. I think that's why I got so thrown off, was like, I think logically I'll find a contradiction. They won't actually be similar, but they would look pretty similar, won't they? They look like the exact same shape, but just different sizes or the same size, right? Remember, if you're congruent, you're also similar, right? You get that for free. Okay, so anyways, let's take a look at this from examples here. I'll actually show you that, yeah, these have to be similar to one another. And we'll prove this very quickly later on once we figure out some shortcuts to actually proving if things are similar to one another. But here we'll be able to get it. So if you remember about similar, right? Similar, all the angles got to be congruent. So looking at these, I have three isosceles triangles right here. And if we mark it up a little bit here, remember, an isosceles triangle has at least two sides that are congruent. And if it's a right triangle, you can only be isosceles. You can't be equilateral, right? If you're equilateral, you're 60-degree angles, right? Since I have that 90-degree angle right here, I'm going to have at most two congruent sides. So I have those two congruent legs, and this is a 90-degree angle, of course, right? We have a 90-degree angle there, 90-degree angle there. Here are my two congruent legs in this diagram. I'm going to do two tick marks here. And here are my two congruent sides in this diagram right here. So first thing with similarity, reminders. First thing about similarity is that, one, all angles have got to be congruent. All corresponding angles, I should probably put that. All corresponding angles have got to be congruent. And they are for isosceles triangles, because you have a 90-degree angle, right? So those three 90-degree angles are all congruent. And then what do we know about the other angles? Well, the other angles, oops, I should have done three tick marks there because I have one there, two there, and I have three there. Well, the other angles in an isosceles right triangle are going to be 45 degrees. Another name for isosceles right triangles are actually 45 90-degree triangles. And how did I get that, right? How did I actually determine that? Well, this is 90 degrees, and these two sides, because it's isosceles, are congruent to one another. And we know from the isosceles triangle theorem that if I have two congruent sides in one triangle, then the angles opposite those sides are going to be congruent to each other as well. So if this is 90 degrees and these, the acute angles of a right triangle, are complementary, right? They got to add to 90 and they're the same, right? And what's 90 divided by 2? 90 divided by 2 is 45. Okay, so that knocks this one off here. Are all the corresponding angles congruent? Yes. Yes, they are. So then the second thing, this is really the thing that I had to really question and really kind of mess with me, I guess, in the particular lesson that I did with you and kind of threw me off, is are all corresponding side lengths proportional, right? Are they proportional? As we go from one triangle to the next triangle, right? The corresponding sides, are they in the same ratio as one another? Are they proportional? Okay, and so we'll prove that for these three of these ones here. Okay, what's easy about this? Okay, what's easy about this is the legs, right? The legs are certainly going to be in the same portion because these are the same. These are the freaking same right here. Let's check this out here. And I drew this on grid paper, right? I wanted to draw this on grid paper because I want to show you that drawing diagrams on grid paper, a lot easier to draw things accurately. Look at this. I drew a right angle right here because that's where the vertical grid meets the horizontal grid. Okay, vertical grid meets horizontal grid, right angle there, and then I'm just rotating it around so you can, I'm not doing any tricks on you. I'm trying to be comprehensive here in my example. So if I do this here, I drew this in a certain way where, check it out here. This length is 4, and again, because it's isosceles, that means the other length has to be 4 as well of the leg, right? Other length of the leg has to be 4 as well. So that's 4, and that's 4. This one here is what? 2. This is 2. Okay, another example that I have here is 1, 2, 3, 4, 5 for this leg. and 5 for this leg. 1, 2, 3, 4, 5. So obviously, right, if we're looking from this triangle to this triangle, the scale factor would be a half, right? Going from that triangle to that triangle, that's a half, okay? Here, right, going from this triangle to that triangle, the scale factor would be 4/5. 2/5 right there, right? That would be the scale factor. So that is at least sticking with two of the sides. What about the diagonals? What about the not the diagonals, the hypotenuse, right? The hypotenuses of these three. Here's the thing where I got a little screwed up, right? I got a little screwed up on this. If you know the Pythagorean theorem, you know how to solve for that hypotenuse, you can actually prove this, right? You can prove this. It turns out that this hypotenuse here is also going to be in that same ratio, okay? In that same ratio. And we'll prove this when we get to Pythagorean theorem a little bit later. Look at this here. This is a little bit over 4, I'd say. Let's see here. But how can I prove it with you is that let's pretend, okay, let's pretend for a second that this here, if this is 1 right here, maybe I actually won't do Pythagorean theorem with you. I'll actually kind of like show it to you in terms of how many of these little diagram tick marks there are. So if I have, sorry, diagonal, like diagonal lengths there are here. So if we let one unit be like the distance between, right, along the x-axis kind of thing, right, horizontal distance, this is 1, that's 2, that's 3, that's 4. If we look at this, a hypotenuse, it's a little bit longer than that. We're going to calculate exactly how much longer, because look at this. This isn't 4 units, right? This isn't 4 units right here, because to go across a diagonal of one of these little squares we have here, right? If this is 1 right here, for instance, and let me do a right triangle right here. If that's 1 and that's 1, this distance here is definitely longer than 1, right? Longer than 1 here. But what can we do actually? Well, this is longer than 1. I don't actually want to prove how long it is. You can prove it, right? We'll get to in chapter 6 when we do Pythagorean theorem and whatnot. We can figure out what this is right here. So what I'm actually going to do to demonstrate this, that these hypotenuses are going to be in the same kind of scale factor as this 4 and 2 is. Like it's going to be proportional with one another, is what I'm trying to say. I'm going to assign this hypotenuse for the base 1 unit here. I'm going to assign it the variable y. Okay, I'll give it the variable y here. So that means for this 4, if this leg is 4 and this other leg is 4 here, this hypotenuse will let this distance be y, okay, which is the 1 unit kind of diagonal across it. This unit is y. This is also another y, and this is also another y. Why did I choose the letter y? Well, I had to define a variable. I could have chosen any variable. I'm choosing y here. Okay, so it turns out that this hypotenuse right here, I'm going to let it represent 4y. Okay, I'm going to let it represent 4y. So here, if this leg is 4 and that leg is 4, this 45, 90 degree, right, isosceles right triangle, I'm going to let the hypotenuse be 4y. Okay, well then question is here, let's look at this one here. Now this is just a length of 2, 45, 45. And what's the hypotenuse distance here? Well, 2 times however much longer, right? One of these one little units is, if we multiply that to get to this y that we have here. So this is 2y, right, for the hypotenuse. Okay, this was 4y for the hypotenuse again here. That's 2y. And what's this going to be then? Okay, well, this is going to be 1, 2, 3, 4, 5, right? 5y, okay? So it turns out, yes, that this proportion here holds, okay? Because here, 4, this side to that corresponding side is in a 4:2 ratio. That side to that side is in a 4:2 ratio. This here would be in a 4y to 2y ratio, okay? Otherwise known as a 4y over 2y ratio. But wait, our y's cancel? It's in a 4:2 ratio, or a scale factor of 2, just like the other sides. This here would be in a 2:5 ratio, just like that side to that side is in a 2:5 ratio here. So you know what? We've proven here that our side lengths are proportional, and all of our corresponding angles are congruent. They're identical, right, for any isosceles right triangle. So I'll go ahead and give one more example, because you're like, Mr. Ford, you're pulling my leg. You chose those on purpose. Give me a number, right? I'll be a magician. Tell me a number between 1 and 10. Oh, did you say 7? Did you say 7? Okay, so let's check it out. So I'll draw one. I haven't drawn one oriented like this down here. So let's do this. 1, 2, 3, 4, 5, 6, 7. And then up here, 1, 2, 3, 4, 5, 6, 7. So now we have a 7, length of 7 for our legs here. Isosceles, right, because I went 7 up. Is that actually 7? Let me see if I actually counted that right. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is 7. This has got to be a right angle because, hey, it's where horizontal meets vertical. So there we got that there. And then check it out. What do we have for this hypotenuse here? Okay, well, we got one of those little, right, diagonals across our base, right, unit here. Okay, right, there's one, there's one. This is going to be y. Okay, one of those, two of those, three of those, four of those, five of those, six of those, and 7 of those. I get 7y, okay? And so that means my side lengths are in proportion to all of these other ones here, okay? Y here is actually going to be radical 2, right? Square root of 2, actually. If you do the Pythagorean theorem here, 7 squared is 49. Another 7 squared is 49, so add them together, you get 98. That square root of 98 actually simplifies to 7 radical 2. So anyways, that's something to look forward to is when we actually do the Pythagorean theorem and solve for stuff. Yeah, we're actually going to figure out the numerical distance here between that point and that point, the lengths of the hypotenuses. Okay, so side lengths are proportional, and what again, right? Are the angles, all corresponding angles, congruent? Because that's the second criteria to get similar figures. And yes, they are. This is a 90-degree angle, right? Because this is a right triangle, and we got 90-degree angles in all those other right triangles. And so if that's 90, base angles of a isosceles triangle are congruent. So those two are congruent, and we know that they're complementary, right? So if this is x and that's x degrees, then x degrees plus x degrees equals 90. So that means x needs to be 45 degrees. Okay, and that's true of any isosceles right triangle. Okay, thanks for watching. I know we had a lot of videos today, and this was a tricky one here. It tricked up Mr. Fortin. I was just like, you know what? I don't think those hypotenuses. We can't prove actually that those hypotenuses would maintain the same side length ratios as the legs would be between those isosceles triangles, but we actually can. So I wanted to correct that for number 10 because I knew I got it wrong in the lesson video today. Email me if you have any questions. Thanks for watching, guys. Bye.